Right. Okay then. So this lecture, what I'm going to do is I'm going to do a review of last week, as always. The unit vector. So that's what we did at the beginning of last week. The unit vector is really important. Do I need to emphasize that more? It's really important. We use it a lot in 2D and we almost use it exclusively in 3D. And when we get to 4D, it is everything. Everything is unit vectors. So basically what we did was we had 2 points. We looked at how you look at work out the differential between those 2 points. So calculating dx and dy, which I'm sure most of you have heard me say about 1,000 times now. Calculate your dx, calculate your dy. Okay, so we have 2 points, we have 2 vectors. We need to calculate the unit vector. First of all, we calculate dx, then we calculate dy, then we calculate the magnitude of the vector. Then we divide our dx and dy's by the magnitude of the vector. That gives us the unit vector. We need the unit vector to do a lot of maths, so it's important you know how to calculate it. Anyone got any questions for me on the unit vector? Catch. Right, the rules for this game are you have to throw the ball. We throw it 3 times. If you get hit by the ball, you have to answer a question. So make sure you catch it. Right? Okay. We're going to throw it 3 times. And then whoever has the ball either asks me a question or answers my question. So my question is, how do you calculate the unit vector? Throw the ball to someone. You have to catch it, otherwise you answer the question. So what is the answer to the question?
You have to first of all work out x and y.
Yep.
And then also hypotenuse.
Excellent.
And then you have to put the hypotenuse to 1, don't you?
And how do you make the hypotenuse equal to 1?
Divide it by itself.
Yeah, okay.
And then you have to work out dx by dy. Dx and dy by dividing x by the hypotenuse, and then y by the hypotenuse.
Excellent. So if you didn't understand my explanation, pretty sure you understood that one. Okay? Right then. Okay. Throw the ball to someone. Okay, next question is going to be, how do you calculate dx and dy? Check it to someone. Is this something like an anti-sports team or something? It's like, we are totally incapable of catching a ball. Yeah. Well, that was 1 throw. 2 more throws. Try and catch it this time, team.
No.
Yeah, okay.
2 for 1.
If you get hit, you have to answer the question. So how do you calculate dx? I've got a point P1, I've got a point P2. How do I calculate dx?
You need the...
I have a point P1 which has a component x.
Yeah.
I have a point P2 which has a component x. What is dx?
It's P2, but the x position of P2 take away the x position of P1.
Excellent. Great. Okay, I'm convinced we all understand this. So the next thing, we were looking at detecting collisions. So, previously we had been detecting whether or not a point is inside a circle, which is easy peasy. I know you all like, that's easy peasy now. So to up the program, basically we changed our bullet from a point on the screen to having a radius. Yeah? So the question was, how do you know if the 2 circles are touching or overlapping. So, how do we calculate our dx and our dy? Same principles, right? We have a p1 and a p2. Dx is p1x minus p2x. Same with dy. That gives us a vector. We calculate the magnitude of the vector. How do we know that the circles have overlapped? The radius of circle 1 plus the radius of circle 2 gives us a specific length. If this magnitude is shorter than that length, the two radius together, then we know that the circles have to be inside one another. And we have a little demonstration of that. If you play around with, I believe it's this. Come on, right click. So we basically have chug, 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 chug. Oh, there we go. Come on, come on, come on. Wakey, wakey. So you have a circle here, right? It has a radius here. Once it gets inside, once these two overlap or gets inside, or even if they're just touching, that is the point at which the two radius exceed the magnitude of the vector between them. Okay. So, confident that you can all do this. If you have not done, touch screens. If you have not done that stretch goal of checking to make sure your bullet, and again testing afterwards, because a lot of people went, I think I've done it, but I can't tell because the bullet's moving too fast and it's too small. And I went, well, if you look in the code, you can slow the bullet down and make it bigger, and then you can test. I want everyone to have done this. Right, okay then. Completing the labs. It's really, really important that you complete the labs, because hearing me speak a load of formula and you might be going away thinking, I remember that, I know that, I can do that. The test is when you sit down and code it. You can work it out on paper if you want to. I'm okay with that. Sure, it's going to take you a lot longer in the long run. It is vital that you catch up on the labs. It is vital that you complete the labs. And if you don't...
He's got PowerPoint on his phone.
Okay. Thank you for that. And if you don't, then the key thing is come and see me Wednesday morning, 10 a.m. And I'm pleased to see, I had some faces last week. It's excellent. Because if you're in doubt, get your money's worth out of me. Again, with the independent learning, I expect every student to make an attempt. Even if you fail, turn up and tell me how you failed. Because it's important. These are the stretch goals. This is what is going to help you later on. Right, okay. So last week I gave you some independent learning. Given 2 points, P1 and P2 in screen space, write an algorithm to plot every pixel in the line between those 2 points. Who's done it? It's not very many. Who's attempted it? Okay, few. Got to make attempts, people. You learned from your failures. This challenge looks very similar to the one before, doesn't it? It looks very similar to what we were doing in the math lab. Not the meth lab, the math lab. I'm going to be careful how I say that. In other words, you have to ask yourself, if we're plotting every single pixel, what is the speed? This is in pixels. The x is in pixels. We've got 2 points. Yeah? This is in pixels. This is in pixels. How fast do we need to travel to plot every pixel?
As long as 1 pixel is 1 unit, then just 1 unit.
Brilliant. Excellent. So the unit vector is it. If you just move by the unit vector through pixel space, you'll plot every pixel you need to plot. Okay, so how do you tackle this problem? What does this problem even look like? So the question is, what units are we working in? We're working in pixels. It's in pixel space. It's screen space. If we want to plot every pixel, what is the distance between each plot? And again, unit vector gives us a vector that we can then adjust the speed of. But the key thing is that we need to go and test our conclusions. And yeah, you can sit there and do it on paper, which is what I have done. I have gone, okay, I have a theory. My theory is that I just need to calculate the unit vector. So what I've done is I've picked some points, and then I've gone and done the maths. Then I've checked my unit vector. Then I've put it in a spreadsheet. Then I've plotted it out on paper. Then I've done it again. Then I've calculated all the maths, checked that my unit vector works out, put it in a spreadsheet, plotted it on a piece of paper. It works. I also wrote the code to do it as well. So, this is the kind of thing I expect you to be doing in your independent time, which is about, I think you have about 4 to 5 hours of independent time for this unit. Adds up for all the other units. It's about 20 hours a week we expect you to work. Don't think that the lab sessions and this lecture are it, because it's not. You have to keep going. Okay, the next point was independent learning part 3, which was given 2 points, and t, which varies between 0 and 1. Write an algorithm that creates a new point such that at t0, tp is p, and at t1, tp equals p2. Right? So, you have 2 points, you have a p1, we have a p2. At t equals 0, we want the new point to be here, and at t equals 1, we want the new point to be here. And at all the values between t is 0 and t is 1, so t.25, t.3, t.1, we want it to be on this line. So how do we go about solving this problem? Because again, a lot of what we do in maths is solve problems. A lot of what we do in games is solve problems. We're given tasks by the designers, we have to solve the problem. So let's consider the edge case. The edge case is t equals 0, tp equals p1. And at t equals 1, tp equals p2. And then we just make some functions up. And this is the magic of maths. You go, I don't know what the functions are. They're a little black box. They could do anything. But I'm just going to call them. So I'm going to call them f, where f is a function of t, that when t is 0, such that tp equals p1. And then I'm not going to have another function g, where g is a function of t when t equals 1, such that tp equals p2. And then again, I've got tp, p1 times ft, where f is a function of t when t equals 1, such that tp equals 0, and tp is p2 times gt, where g is a function of t when t equals 0. And basically what that means, because that sounds like a lot of information, what this means is tp, when t is 0, wants to be equal to p1 plus the value of p2. But we multiply p2 by 0, because p2 by 0 is 0, and therefore we end up with p1. Similarly, when we're here, we want to make sure that tp is p1 times 0 plus p2. So, what we end up is an equation that says tp is p1 times f of t, function t, plus p2 times g, which is a function of t. We don't know what these functions are yet, but we have a formula. And you will see this formula come up time and time again in terms of, I want a solution, I've got 2 outline points, I need to derive formula or functions that solve that problem. And we can clearly see that when TP equals P1 times 1 and P2 times 0 when T is 0. Yeah? So when T is 0, this P1 is here. So it's P1 times 1 plus P2 times 0 because P2 is here and we don't want any of that component. And when T is 1, TP is P1 times 0 because we don't want any of that component plus P2 times 1 because we want all of that component. And then we can look at this and go, hang on a minute, is there a relationship between this value 1 and 0 and 0 and 1 so that we can plug in T into this equation? So we've got Ft, which is this bit, is 1 when T is 0 and Ft is 0 when T equals 1. And GT is 0 when T is 0, and GT is 1 when T is 1. So this looks really easy. GT is 0 when T is 0, and GT is 1 when T is 1. That gives us our answer right there. So we can say that the function for GT is simply T. And the function for T, for Ft, is 1 minus T. So we substitute those functions in. So our substitution is the final formula is Tp is P1 times 1 minus T and P2 times T. This is a super useful formula. And then what I've done is I've not made assumptions about my formula being correct. I stick the values in and I test, and then I can also code it. This week, I'd like everyone to do this. And if you get stuck, or you think I've just spouted witchcraft, then you come see me and go, I did not understand that. For the brave, who doesn't understand that? Wow, that's a lot of brave people. Okay. Go back to the beginning. Can I have a... No, I want a pen.
When you say like TP equals P1 times FT, and when you're putting T0 into that, you not then put 0 into TP, so it's 0. Whereas TP is TP meant to have an arrow.
Let me go through it. This is tough stuff.
But hard to understand, because I get that a lot with, like, when you substitute letters in sentences, I can't keep up. I have to remember what each of those letters represents. And by the time I remember the first one, I've missed the entire sentence.
Yeah, it's okay. It's okay. This is going to take a while to explain. I'm going to run through it again, and then I suspect on Wednesday morning I'm going to be inundated with people still. This is complicated stuff, and it doesn't appear apparent the first time somebody says it because it's a lot of gobbledygook, and I will try and simplify. We have a point P1 and we have a point P2. Okay? And what we have is another value called t. Whoopsie-daisy. And t goes from 0 over here to 1. So you have this value t, and it goes from 0 to 1, up and down. And t can be anything between 0 and 1. And I'm saying to my little black box, and my little computer, death trap. I'm saying to my computer, if I give you the value 0, give me the value P1. And if I give you the value of 1, give me P2. And if I give you the value of 0.5, give me halfway between P1 and P2. So that for any value of t, you will plot along this line, which is very similar to what we have just done with the unit vector plotting every pixel. So t is just a variable, but it drives between P1 and P2. Now I need to work out what that formula is, and it sounds complicated. So let's consider a simpler case. P1, P2. Let's give this a value of 4, and let's give this a value of 16. And let's consider t. So we can definitely say t0 is 4. And we can definitely say t1 is 16. And now we can definitely say that 8, no, it's 12, 6 plus 4 is 10.
Yeah, halfway is
10. So we can definitely say t 0.5 is 10. And we want a formula that will do every single point, not just those points. Not just me calculating in my head, which is not good. You don't want me running your graphics card. Right. Okay. So we can say that t at 0 is p times something, which has to have something to do with t, yeah? And we can say plus P2 times some other crap. Definitely a different crap. Not the same crap. Two different things. Right? And we can say for certain that at T0, P1 is P1 times 1. Yeah? Plus P2 times diddly squat. Right, because P1, which is 4, 4 times 1 is 4. And P2 times 0 is 0. And 4 plus 0 is 4. So that works for that particular case. Okay, now I need to make it work for another case. Go away line. So let's say that t at P2 is equal to some form of p times something plus P2 times something. And this is t at P2. So it should equal P1 times 0, because we don't want any of the P1 value, plus P2 times 1. And let's try that out. P1 is 4 times 0, which is 0, and P2 is 16 times 1, which is 16. So t at P2 is 16. So that works out. So now we want to just test one mid position because we know the answer is 10. So let's do that. So t at 0.5 is equal to P1. It is some function of t. We know this is what it's going to end up. But we also know it's P1 times 0.5 plus P2 times 0.5. And P1 times 0.5 is 2. And P2 times 0.5 is 8. And 2 plus 8 is 10. And that is awesome. It works out. So we now have some idea. But the thing is that we've got to express these values not as actual numbers, but as parts of t. So let's do it as parts of t. Tp is equal to P1 times a function of t. And in this case, the function is 1 minus t. Yeah? And the reason it's 1 minus t is because we want, when t is 0, we want 1 minus 0, which is 1. P1 times 1 is 1. When t is 0.5, 1 minus 0.5 is 0.5. So we have P1 times 0.5. And then when t is 1, 1 minus 1 is 0. P times 0 is 0. Similarly, for P2, it is simply times t. And again, we can check this. When t is 0, we want P2 to be 0, and P2 times 0 is 0. When t is 0.5, P2 times 0.5 is half of P2, and when t is 1, P2 times 1 is P2. It works out. Is that a question?
Yes.
P times.
P times, right?
Yeah. Right. I will press on because now we have to do it in a more complicated way. Hopefully you've got some grasp of this concept that we have two extreme values, and the idea is that we can integrate between those two values based on a value in between. You might put that in the back of your head for the moment. We need to rotate points. So given a point P and a rotation A, we need to create an algorithm that will compute a point P dash such that P dash is P rotated by A. So basically what this says is we want to be able to rotate stuff. Because if you look at our asteroids game, there's a ship and it rotates. And that's how we shoot stuff. And it's a good idea to know how to rotate stuff if you're going to do games. Otherwise, it's going to be a weird game. I think that, even Tetris has got rotation, though it's fairly arbitrary. So first of all, we have to consider the arc as a distance. Let's just open this up. I've got no middle mouse click. That's weird. Okay then. So, again, you can follow the link to this. Sine and cosine, basic trigonometry. Some of you will be familiar with this, others maybe not so. It was in the distant past and you have forgotten. You have to bring it back now. You have to regurgitate it. Consider that we have a vector. And in this case, this is a unity vector. This is of length 1. As you can see, it sits on the circle 1. Yep. Okay. So what is interesting is if we compute the dx and dy. So CE is our dy and CF is our dx. And so we can compute our dx and our dy values. And I'm also computing down here the sine of the angle. And you're going to see something really interesting, but, maybe not so. Interesting for those who love maths.
Yeah.
Dx is, in this case, 0.4875, and the cosine of x is 0.4875. And the sine of the angle is 0.873, and the length of the dy is 0.873. Is this a coincidence, you ask yourself? Holy crap, I don't think it is. Look.
Wow.
This is where sine and cosine come from. They are merely the lengths of the opposite and the adjacent on a unit vector. And of course, if we're not dealing with a unit vector, if we're talking about some arbitrary circle that's a bit bigger, let's go and make a equal to 2. And then we go and look at the sine and the cosine and the relationship. You can see that our dx now is 1.79 and our cosine value is 0.899. I'm sure if you multiply that by 2, you get that. Similarly, our y value, or our opposite, is 0.436, and if you multiply it by 2, you get 0.8. So this is where sine and cosine come from. They are merely ratios, and that's where they're derived from. And this tells us exactly how to rotate a point. Because obviously what's happening is we're integrating from point A here round through the 90-degree angle, and we're just going through all of those combinations of sine and cosine as we go. And that is what a rotation is. So we're changing the value of sine and cosine, and that causes it to rotate. Mind-blowing. Okay then. That gets us some of the way. We know that it's going to involve sine and cosine. If we want to do this rotation, we should consider the edge cases because we're going to derive this formula. I'm deriving it from first principles. I'm showing you the origins of it. You need to know the formula. If you can derive the formula, that's excellent because that will help you in levels 2 and levels 3. At levels 1, you need to know the formula, which is why we've given you the books so you can write it down. But let's consider the edge cases of 90-degree rotations. Let's consider the value of 4 in the x and 1 in the y. And what happens? Ooh.
Pleasant.
Ouch. Right, and what happens when we rotate this 90 degrees? So you can see that this is x value 4, y value 1. We go and rotate it 90 degrees, something interesting happens. The y value is now the x value. But the x value is minus the y value. You can see that here y was 1 and here x is minus 1. If we get round to 180 degrees, you can see that our x value is now minus and our y value is now minus. So we have -4, -1. And then we get round to here, you can see that what we have is our y value is our minus x value. And our x value is our y value. So in order to be able to rotate 360 degrees, we need to be able to shuffle all of those values around. So let's just have a look. So what I've done here is I've just plotted it all out. I've got my x value is 4, and where it is at 0, 90, 180 and 270. I've got my y value, which is 1, its value at 0, 4, 180 and 270. I have my cosine value at 0, it's 1, at 90 it's 0, at 180 it's -1, and at 270 it's 0. And you should probably be able to picture in your head that the cosine curve, if it went along this line, kind of starts off at 1, drops down, gets round into the negative, comes back up again and repeats. Sine, on the other hand, starts on the axis at 0 and goes up and then goes down. So our sine value starts at 0, goes up to 1, goes down to 0, goes to -1 and then repeats. Right, now comes the tricky bit. Because we have to consider what happens to the rotated p-value. So the rotated p-value basically is a function of x, and a function of y, and a function of y, and a function of x. We have to make these things work out as we had to previously when we were integrating along a line. And we can work out that at 0, x is x times 1 and y is y times 0. And y is x times 0 plus y times 1. That one seems really obvious. In other words, x is x times 1 with no y. And y is x times 0 plus y times 1 because there's no x. Yeah? I can. It'll break everything horribly. Wait. Okay then. So, at 0 it's easy. X is x, y is y. And we need to eliminate these. At 90 degrees, x is minus y. That's the tricky one. Y is merely x. At 180 degrees, x is minus x, and y is minus y. And then when we get to 270 degrees, x is y times 1, and y is x times minus 1. So how are we going to get these values out of sine and cosine? Especially when you consider that they don't line up. Because here's our problem. At 90 degrees, sine is 1, not minus 1. And if you remember, we're rotating here, we get to here, our sine value is 1, but our x value should be minus 1. So we know that we need to negate this component, which is the tricky thing, but it's the most significant thing when you look at the formula. Here's the formula. This is a really important formula. This is a way important formula. You need to know this formula. It's a good idea that you somehow have a way of recalling this formula when you get to the math lab.
Is there a power on this?
I would attempt to zoom even further. It is in the notes for the lecture as well. Okay. So x is x times the cosine of a minus the sine of a, and y is y times the cosine of a plus x times the sine of a. The tricky one is the x value. It's the one with a negative sign in it. You'll notice that as I've written this out, the x and y columns don't line up. And then I've rewritten it so that the x columns line up. And you go, why the hell have you done that? That's a complete waste of time and the formulas are the same. The reason that I've done that, and I should press that button, go away. Right, the reason that I've done that is because when we come to matrices, x values have to be in one column and y values have to be in another column. And you'll see how this formula gets transposed into a matrix in a further lecture. Right. So, there is not that much to do. Basically, you have two pieces of code. You have a rotation around a point, and you have a rotation around a line. For some reason, I haven't put the links in, so I will do that when I get back to my desk. Sorry, I'll go over that. You have two pieces of code. The first piece of code is a point. I want you to rotate that point around an axis. So that's applying the formula. The second piece of code is a shape. I want you to scale the shape, and I want you to rotate it around an axis. Right. Several people have asked me about what's the exam like, what kind of questions, and now is a good time to show you what the questions are going to be like. This is your independent learning for this week. I want you to go through these questions, work in groups if necessary, because, you know, a shared brain is a lonely brain, whereas at least if you get your brains together, you might be able to help one another. Ultimately, you get stuck. Wednesday mornings. So we have, you might recognise that at some point I asked you to find the definition of these things, and maybe you wrote them down in your book and maybe you didn't. Calculate the magnitude and unit vector. So given a 2D vector, calculate its magnitude and unit vector. So you're writing formula or pseudocode. The next one we have is given a ball, do some stuff with it. Then we have a firework, then we have a bomb that goes off, and then we have a bit of integration. If you have not completed all the tasks or are struggling with any of the unit, come see me Wednesday morning at 10 o'clock. There's the lab challenge. So from the given code, complete the function. Oh, there's the link. I knew I'd put it in somewhere. So basically, in the code, there is a function, rotate vector, returns a vector 2, which is why it's got this. This is a function. This is what it's called. This is what it returns. And what you provide with it is a vector and a float. So basically, you give it a point and an angle, and then you work out the new point and angle based on its rotation, based on the formula that we've just done. And then the stretch goal is transforming a shape. So basically you're given 3 transforms: the translation, which is a position movement, a scale, which makes it bigger or smaller, and again rotating the point. There, all the functions are written out. They've basically just blanked where the code goes. Then I want you to play around with the order of operations and see if it makes a difference. And then change the vertex list so that you can draw your initials just for funsies, because it's all about the fun. And then the independent learning is complete the exam questions that I have provided, work in groups if necessary, and review the asteroids code, then I'll put the link up. Any questions?
What is A in that formula from before?
The angle.
Okay, yeah.
Rock and roll, yes.
How long are you there for?
Until I've finished answering all the questions. You can't, right. So let me put this into perspective. I guarantee to be there for 2 hours, 10 until 10:12. Yeah? Well, I can do math. Don't ask me if it's AM or PM though, because that one trips me up every time. I'm there at 10, I stay for 2 hours. If nobody comes and sees me, I bugger off. Right? So if you turn up at 12 and I'm not there, it's because nobody's seen me and I've got all lonely and sad and I've had to go and find some friends. But if you turn up between 10 and 12, I guarantee I'm there or dead. Take your pick.
Which class? 12.
Pardon?
Busy.
So when can you come to me?
Immediately after 12.
Immediately after 12 will do.
Immediately before 10. No.
Yes, but if you come and see me before 10, you'll be going. I've got to go now. See me after 12.
You said you already got.
Probably won't be in your case. I'm going to leave it another 10 minutes just for you. Okay?
So where do you want to be? Wednesday, where?
JM 505.
Chamber 505.
Yes.
Where?
It's in the building next door on the top floor.
Which? Oh, okay, he has the same person.
The room. JM 505.
Okay, fair enough. I guess we'll see you.
See you
there then.
Wednesday.
Of course. So can I get also the notebook on Wednesday as well?
Yes.
Thank you very much and sorry about that.